My name is Gustav Fick. I'm the subject matter expert for 3D scanning and UAV at Optron. And ultimately, the ExynAero system will reside in my portfolio. And today I'm joined by Joel Vene. He is basically the sales executive at Exyn. So thank you so much for joining, Joel. And we're really looking forward to this partnership. So guys, just a couple of house rules. Please mute yourself. If you have any questions during the course of the presentation, please feel free to raise your hand. And, let's attend to that question, as soon as possible. But ultimately, enjoy the session. It's going to be an interactive session, so please feel free to really kind of make use of this opportunity. And then also, please just switch off your cameras. And then if you also have questions and you want to maybe just use the chat room for that, you're also more than welcome to do so. Once again, the recording will be available. So for the guys that might, if you want to recap on this and maybe review it again after the session, it will be available. All right, guys, so ultimately, let's get started. So guys, today's session, we will be covering the ExynAero system. It's basically an autonomous aerial robot. So the objective for today will basically be an overview of the system. What does it actually do? Why do you use it? And we're going to basically then just cover everything that, just go in deep detail into the system. And then what we're going to do then is basically to move over to how do you actually do a flight mission, showing you how to do the data capturing process in a simulator, and then also how to get your data georeferenced. Once we get to that part also, what is the kind of deliverables that you can expect to get out of the system, and then just show you some success stories on this. So guys, I'm going to now hand over to Joel, and we're going to be running through the presentation. And once again, please feel free to ask any questions if you have any. All right, over to you, Joel.
All right. So hello, everyone. I'm Joel. I'm from Exyn. I'm based out in Canada, and I'm the sales executive for Exyn Technologies. So thank you, Gustav, for the introduction. And as Gustav mentioned, please do ask questions at any time. I will speak a lot, so don't be afraid to put that hand signal up at any time. It's pretty hard to wait for me to be done speaking, as I tend to always be speaking. So don't worry about the question part. And as you mentioned, we're going to be touching base on the ExynAero, which is the flagship mining product here at Exyn, an autonomous aerial robot. And it's actually the world's leading, most advanced autonomous aerial robot available on the market. Gustav, no worries. Just quickly sort this out. No worries at all. Here we go. Okay. Perfect. You want to put to the next slide? There we go. All right. So a quick background on Exyn. We were founded in 2014 in Philadelphia, in the United States, and we've been working on a prototype version of the ExynAero since then. And ever since 2018, 2019, it's been a industry-used robot in various sites across the world on every single continent except for Antarctica. So we have been put through our paces, and it's really now becoming an integral part of an operations day-to-day use cases when it comes to mapping and scanning for any areas. All right, so we're going to dive right in here. I'm sure most of you are familiar with pictures such as the one depicted on your right. Traditional cavity monitoring systems, or CMS systems, often involve stationary units, right? And they have many drawbacks. The main one being they're quite dangerous in the way that the workers have to be very close to a stope opening, also known as the brow. So putting workers in danger, very near dangerous areas, and it's ultimately that's the one major drawback of the system. Secondly, there's also danger in terms of just the physical work, how heavy the equipment is. It can lead to some injuries. It's also very inefficient. Takes a long time to set up. It's not very practical at times. You can only get one stationary scan, right, from either the bottom or the top sill. And it's also quite limiting in terms of the data you do capture, even after you perform that longer scan. So How does the ExynAero compare? It's really, there's three main points to take into consideration. The first one being the efficiency. Is that someone who has a question?
No, it's somebody that needs to be admitted.
Okay.
Thank you, Etienne.
So one of the first points being the efficiency. So compared to traditional systems, you're not going to be looking at hours of operation. You're going to be looking at approximately 15 minutes. That's from unpacking to completing the mission, which typically a stope mission, it would be about approximately a flight of 1.5 to 2.5 minutes. Packing it back up, you're looking at 15 minutes. Secondly, much less hardware. You don't need to pick up full of equipment, simply one case with the drone in it. Very easy, one-person operation. But the main point is the safety aspect. No workers have to be near to the stope opening or the brow opening. They can stand a good 50 meters away from your stope in a very safe location, and they're able to perform an autonomous scan at a touch of a single button. So the safety is really where you see that big advantage on your day-to-day. And lastly, of course, the quality of the data. So, of course, if you're able to get a full scan of your stope as the drone is able to go up into the environment or down into the environment, depending where you're starting from, you're really able to identify any underbreaks or overbreaks, which in the long term will allow you to either be able to identify any missing ore you might not have captured, or identify that you may be overbreaking and you're spending some of your valuable resources mucking and transporting, at the end of the day, some waste, right? Also, the volumetric calculation for backfill calculations, this will get you the most accurate volume calculation in the market. Lastly, there's also the georeferencing side of it, which lets you be able to compare your design to your actual stope design. And again, just critical data that gives you much more advantages compared to a traditional system. All right, so on to the next slide. Oh, my apologies here. I seem to have moved my, oh, right here. Okay, perfect. So let's take a quick look here. The left cloud on the right, which is titled Traditional CMS, you can see here has approximately 50,000 points according to the slide. It took approximately an hour or more of operation in order to perform this scan. And of course, the workers are quite at risk. They have to hold on to the system or get very near to the opening in order to capture this data. When you compare it to the second cloud on the right, which is an ExynAero point cloud, you can see that you have many more points, 50 million points to be exact. It's a much more complete scan, and the entire operation took approximately 10 minutes from unpacking to repacking, the flight itself only being a couple minutes total. So the great difference here is actually the volume. We see that a typical stope scan, when you compare the CMS to the ExynAero, you're looking at about 30% of volume that is missing from the traditional scan, 30% being a very large discrepancy. So of course, this is survey-grade data, no shadowing, and it's all real time. So you're getting that data transferred to you as the robot is flying. You're getting a full look at your environment, and it's really the top-of-the-line product nowadays in terms of survey and stope scans. All right, so let's take a bit more detailed look at the product itself, the ExynAero. What is it? What does it look like? So this is the ExynAero itself. As you can see, it's a DJI M210 airframe. And essentially what we do is we add on our payload, which enables the full autonomy, the ExynAI we call it. So at the bottom here, the green, as you can see, with the LiDAR at the front, this is pretty much the Exyn payload. This is what makes it autonomous. It holds all that software that makes it a fully autonomous platform. Essentially, ExynAI uses an algorithm called the SLAM algorithm, which stands for Simultaneous Localization and Mapping. The ExynAero is able to capture the data with the Velodyne LiDAR at the front. It's able to capture the data that you want, all at the same time using that data to actually plan its flight path and plan its mission, go around your cables, your obstacles, around dog legs, around corners. It's all done through this payload. Of course, we also have two LED power lights that you can see are marked here right beside the Velodyne LiDAR. Those lights are not necessary for the drone's operation. They are really only there for the 4K camera, which is the GoPro mounted at the top of the unit, which allows users such as yourself to actually get a video and a visual on the areas you're scanning. So you can get an actual video of where the robot is going, and the lighting, of course, provides that light that you need in order to capture that video appropriately. All right. So touching base again, this system is fully autonomous out of the box, and it doesn't need any support whatsoever on your end. It doesn't have GPS, it doesn't need GPS, it doesn't need any Wi-Fi connection, it doesn't need any prior maps. You don't need to give it any, you don't need to load in any maps of your mine, you don't need to load in any coordinate points or coordinate systems. You really just give it a very general idea on where you want to scan, and it will perform that mission in real time for you. So again, it's really out of the box, a full system that doesn't need any human help. No one's going to actually be piloting this with 2 sticks. It's going to be fully autonomous and controlled through the tablet that you see on your right. And of course, beyond line of sight, which is a big advantage compared to piloted systems, you can go around your dog legs. You can go into multiple different drifts, up into your stopes. You don't need any visual line of sight. In fact, once the robot takes off, I could essentially break that tablet in half and it wouldn't really care. It's fully standalone. It doesn't need any input from a human or from anyone for that matter. It's going to perform that mission without any support whatsoever. A quick overview of the operation, and I'm going to go through this slide rather quickly as we're going to be touching back on this further on in this presentation. You're going to get to see a full example. So essentially all it is you establish a quick mission plan for your robot, a very generic plan using a 3D volume. From there, you perform the mission. So you simply press play and let the robot fly. Next, you download that file or that data from your ExynAero onto your tablet locally. And next, from there, you can finally do your georeferencing, your post-processing, and you're able to export that into any third-party mining software suite you want to use that data in. All right, so we took a great deep dive into the first application, which was, of course, the survey scans and the stope scans or any environment that you wish to capture data on. There's also the search and rescue side of things. So for search and rescue, if you have to go into an environment, so if there's a collapse in a mine or something of that sort, you're able to use the system to identify that area. Of course, everyone, please let us know if you're able to see this video play correctly. If not, we'd be more than happy to share the actual video link. So this is a real-life example of a collapse in a mine. We were contacted by this mine, and we were able to ship them out robots in a very quick manner. This wasn't an existing client. We trained them up virtually on a video call such as this one in under 20 minutes. They had never used our platforms, and they were able to perform this fully autonomous flight and capture very much needed data in real time, right? So you can see here the drone's actually flying autonomously inside the collapsed area. It's getting a full scan of this environment. So of course, what this enables the search and rescue team to do is that they're able to really get an idea of what everything looks like, what equipment they're going to need, and it really lets the search and rescue team put a full plan together without having to put anyone in danger and have to go see what it looks like, and of course have no idea what they're getting into. Here, you have a full idea of what they're getting into. You saw the robot maneuver into that space fully autonomously. No one's piloting it. Now it's returning back home, and you'll be able to see just how safe and how a great distance away the operators were able to stand. And of course, I reiterate, this wasn't an existing customer. This was their first time operating this unit under a pressure situation with 20 minutes of training total. So it really shows you the ease of use of our system. And just bear with us. We're going to go back towards the presentation. There we go. So we can go to the next slide. All right. This brings us to our third use case. So many mine sites have stockpile storage or dry ore stockpile storage on surface, which is often covered or in a big dome, such as the ones represented here. And one use case we saw actually in real time in Canada was the mine site having to shut down their conveyor for a surveyor to come into the dry ore storage. They had to complete scans with their total station, which took them about 4 hours. So that's 4 hours of sorry, I forget the word, the conveyor belt being turned off. So that's essentially 4 hours of the mill not processing that ore that you've been collecting. And essentially, that would cost them approximately $50,000 per month, or every time they did this scan, $50,000 of lost time. And essentially, they're able to use the ExynAero to perform a scan in about 1 minute to 2 minutes, and essentially be in and out and save them that entire lost time. So regenerate that revenue that they had lost on since they had to shut it down for so long. So that's another use case. So here we just have a few more examples of point clouds and the data. You can see really just the definition and the amount of points you're able to capture. This is what it would look like in your mind in real time as the robot flies. And it gives you kind of an overview of what a stope looks like, a stope scan looks like in detail from the ExynAero. All right, and here are just a few quotes from some of our customers. One of the big ones at the top being Dundee Precious Metals. They've been using our system for over 2 years, and it's actually now the only survey system they have on site in terms of 3D point cloud scans. It's the only one they have on site. It's the only one they rely on, and they use this almost multiple times a day. It's part of their day-to-day operation, and it's their most important tool when it comes to scanning. So it really took over from traditional systems. Of course, on the last quote at the bottom is from Vale North America. So Vale and Agnico Eagle are big mining operations. They have multiple sites all across Canada and North America, and every single one of their sites has one of our systems. So it's really becoming an enterprise solution for them. And next, so here, this is just a video library. We're not going to be touching these videos today, but of course, at the end of this presentation, if some people want to see more of these videos, I can either send you the links or we can watch them together and I can walk you through them. But since we're going to be doing a real virtual demo here on the simulator, we'll go ahead and skip this slide for today.
Good. All right, guys. So yeah, ultimately, up until now, is there any questions maybe? And also thank you for the guys who's currently attending. The guys who came in a little bit late, yeah, thank you so much for attending. So this comprises the overview of the system. So I don't know if there's maybe any questions. So what's going to happen now? We're going to now move over and actually focus on the mission planning and the data capturing aspect. So please feel free, guys, once again, for the guys who joined a little bit late, please feel free to ask questions. I'm now going to hand over to Joel again.
Nani has got his hand up.
Yes. Right. Please.
Thank you very much for the system. I just wanted to know, do you have anyone in the region who is currently using the system so that we can go and see it working in an underground situation? Thank you very much.
Hi, Nani, it's Shane here. So we have just delivered one of these systems to Katanga Mining in the DRC, and we are in the process of conducting the training in early Jan, and we are happy to introduce you to them if you have to talk to them and discuss the solution.
No problem.
And then in addition to that, Nani, we also have Abuasi Anglo Gold Ashanti in Ghana. They've been using the system for plus 8 months, and they are also, happy to communicate with you if we have to connect you with the chief surveyor for Anglo Gold Abuasi Mine.
Thank you, Shane. Please do.
Thank you, Nani. I will action that from my side.
Perfect. Yeah. So thank you for that, guys. So Nani, is there any other questions, guys? Okay, I'm now going to hand over again to Joel. Oh, there's a question. Yes, sorry, guys. There's also, we've got visitors in the boardroom as well, so bear with us. We're multitasking here, but yes, sir.
Thank you very much. My name is Austin Matei from Sabah. From the presentation you've just done, it looks like the machine is localized. There's no chip involved.
That's right.
How do you provide checks to the machine?
So ultimately, so the thing is, you will use your existing control points. Okay. So for basically what you will do. So when you fly, and this is the part that Joel will touch on a little bit, but you will make use of your control points to actually get your data geo-referenced so that you can now compare the design versus the as-built to compute your underbrake and your overbrake. So those are the kind of checks that you would now do in a typical stope mapping scenario. But once again, we're going to take you guys now through the whole process of doing a mission planning, executing a mission, capturing the data, creating the final georeference deliverable data, then that what will ultimately be used to calculate your final volumes or whatever the case might be. All right, so let me take you guys through that quickly. Joel, I'm going to, yes, sorry, we've got another question.
Yes.
One last question.
I'm going to be there up to the end of this presentation because I didn't plan about it. My name is Augustine. I'm based in DRC. I'm providing a survey as a subcontract service to many companies. We are doing the drone survey. We are doing the survey with the GPS and whatever. I'm very, very interested to underground drone survey because they are very big project developed in DRC.
Okay.
Even they are using like in Katanga, for example, now we are busy discuss with Katanga Mining for all the open pits to do the verification and month for what they are the subcontractor are doing like production those mines.
Okay.
So I would like to know what is accurate of this drone.
So your typical accuracy, so the relative accuracy on the sensor, you're looking at about, it's anything between 1 to 3 centimeters. Okay, that's your relative accuracy. It's because of the Velodyne sensor that it's using, okay, the way that it's capturing the data, that's typically the relative accuracy that you're looking at.
So is it a LiDAR?
It's a LiDAR system, yes. So it's got a LiDAR system that's on there. So once again, when we do this whole mission planning, we actually have a simulator that we're going to run so you can see how it's capturing the data. Okay. So I'm pretty sure you guys are going to find it very, very informative. And Nani, you had another question there?
Yes, I just wanted to know, is there flexibility in terms of the sensor that you can use on the drone? I know you're using LiDAR. If I were to want to do any other form of survey, will I be able to? Is there flexibility on the sensor?
Is it, Nani, are you referring to taking off the payload and putting another payload on, for example?
Yes, I'm referring to that, yeah.
So this is a solution, right? So for instance, the drone and the LiDAR sensor needs to basically be kept together at all times, right?
Okay.
So it's not advisable to remove the payload from the drone. So ultimately, you have to keep the system as it is. Okay. It's very important for the calibration parameters that's associated with the LiDAR and the offsets on the actual drone. So it's preferred and highly advisable to keep the system as it is.
Thank you.
Okay, guys, I'm now going to hand over to Joel, who's now going to share, he's already sharing his screen. Etienne, can you maybe just give me a heads up if you guys can see Joel's screen? You should be seeing a mission planning process.
Yeah, all good on my side.
Fantastic. Thank you, Joel. Oh, you might not be seeing it on TV, right? So let me.
Just bear with us 1 second. We're trying to make sure the TV's in the meeting room is actually.
Table there.
Oh, yeah.
Well, guys, we're just sorting out this spot. So what I'm going to do, sorry guys, just bear with us. I am going to just do this, and then I'll just turn the screen around. All right, okay, we go.
Right. So here we're going to take a look at the ExynAero software, which is what you're going to be using in order to perform a mission, in order to post-process, georeference. Everything's going to be done here. So you can see we kind of have a 3D space here, just a generic 3D space. And we're going to pretend that we're underground today. We're at a stope face. Well, actually, sorry, we're at a very safe distance from a stope. And we're going to be performing a mission. So here today, the first thing I would do when I'm underground The 00 here represents where the drone is starting. I would essentially just simply turn on my LiDAR and get a quick little scan of the environment as the drone is stationary on the ground. I'm going to use that data in order to plan my flight. So bear with me. The LiDAR is turning on in the simulator, and you can see here in real time the data coming in from the drone as it is performing a scan on the ground. And we're going to use this information in order to do a flight planning. So what exactly is flight planning, and what is this cube here that you see? So this cube represents an Explore volume. And what essentially is Explore? It's the highest level of autonomy you can give to a drone on the ground. It's actually the only autonomous drone in the world that has this level of autonomy with this specific use case. So this big cube here represents a goal, or what I want the robot or the ExynAero to scan for me. So you can see I can move this space around. I don't even need to know where the scope is. We're just placing the drone. So here you can see I'm placing the drone facing towards a stope. So if we were there on the ground right now, we'd be looking towards the stope opening, and the drone is facing towards that stope opening. So all I'm going to do is I'm simply going to go here and just create a big box where I think the stope is approximately. I'm just guessing, but I don't need to be very accurate here. The drone is fully autonomous. It'll go around obstacles, cables, anything like that. It doesn't need any of my help. So as you can see, I'm simply expanding my volume, and I'm telling the robot, hey, I want you to scan anything that's inside this volume, and when you're done, come back. So that's it. I'm really going to expand it here, make it really big, just so you can see that I really don't need to give it any specific targets, right? It's going to do it fully autonomously. So here we are. That's it. Our mission planning is done. Now we're ready to actually fly. So I'm going to put myself behind the drone here. We're just going to follow the drone as it flies. And you'll see that during an explore mission, the drone is going to take off, start its mission, and it's simply going to explore within the actual stope, go from corner to corner, and make sure it scans the entirety of it. Of course, the drone is able to pick up points from approximately 80 meters away, so it doesn't need to go very close to any walls. It doesn't need to go very close to any pockets. It'll simply get the full scan, and it'll approach certain areas if there's shadowing of any sort. So here we are. I'll start my LiDAR. And you'll see on the right that these grayed out icons, the top one is going to become green, and it's a play button. And that's really all I have to press to start my drone scan. So once the drone is initialized, I'll press and hold this play button here. And now my drone will take off and start its mission. So of course, you're underground. No one needs to help it whatsoever. You might even lose connection to the drone because it'll travel so far away. That's no problem. You can see the drone here is maneuvering, and now it's starting its explore mode mission. As you can see, it's giving us a trajectory, its intermediate goal, and you would see this in real time underground. As you're there, this is what I would see on my screen in real time. As you can see here, the drone is maneuvering inside this space. It's coming up with its own flight path, its own trajectory. You can see here it's generating this 3D point cloud in real time. At 600,000 points per second. And you can see just how big I made the volume compared to the actual stope. It doesn't matter. It knows what it can scan, where it can't go. Here we are. It's going to enter this space up here. And bear with me, my computer is having a little trouble, so the drone would actually be moving a little quicker than that in real life. It's simply my computer that's getting a little warm. Bear with me. And now the drone is pretty much almost done its explore. It's going to go towards this pocket where there's some shadowing here. So it's going to turn around, move towards this pocket. Just see if I can close a couple things here to get my process time a little quicker. So again, it would move quicker than this in real life. It's just my computer that's, there you go. That seems to have helped it out. So here we are. Now you see it's entering this little pocket on the top because it had a shadow. So that's the beauty of the Explorer. No one's actually giving it a specific mission target or any specific path. It's going to come up with its own path. So now the robot deems that it's done scanning the entire stope, and it's going to come back home. So you're going to see it's going to make its way down back into the stope and back towards where it took off and land back at the original point it started. So again, bear with me here. My computer seems to be a little bit slower than desired here today. So let me see if I can close a couple more things to help us out. The robot moves at approximately 2 meters per second, so it is pretty quick. You see it's making its way back down towards the stope opening. And it's going to go and actually land. So you can see here, while the robot's still flying, we're going to take a look at our data. You can see how just the detail you're able to capture of your stope. You're not missing any shadows, nothing at all. It's fully captured. And of course, this was only a 1.5 minute, 2-minute flight. The robot didn't need any help, any support from the users. And it allows you to really just create a fully, a very good scan here of my stope in the area I wish to plan for. So that's pretty good. I'm going to cancel out of this simulator, and we're going to move ahead towards the post-processing and georeferencing process, which essentially, when the robot lands, as you see, it's coming in now. And just saying, my computer was a little slower. In real time, the drone would be quicker, as it's not depending on this computer to run it. So you can see the drone's making its way towards the takeoff point again. And when it's here, it's simply going to turn around, just like so. And it's going to land autonomously exactly where it took off. So very ease of use. No one's going to be doing anything here. It's fully autonomous. All right. So once the robot lands and the mission's complete, I can download that data directly off my robot. And I'm able to start doing the georeferencing process that I want to do. Any questions so far? Did this make a lot of sense? Everybody understands the general process here for mission planning? It's quite simple, easy to use. So I'll just give a minute here to see if anyone has any questions.
Yes,
We've got a question here.
yeah. The machine sound is very interesting.
Mm-hmm.
I'm just wondering, is it possible to introduce it outside the mine, whereby after doing a flight plan, defining the parameter, then I can send the drone on its own without controlling it, then it gives me what I want.
So are you saying, can you control it remotely?
No, say it can work like what it does there, whereby you send it, it defines its path without any human interference, then it will come down the way it started from. Can I do it? Maybe say I'm doing a topo survey with a defined area. Rather than me controlling, say I'm supposed to control it going back and forth, I just leave it to do its work. After when this is done, it comes back.
So ultimately, this the solution is for indoor scenarios, okay? Because it's relying on basically the 360 map that it's basically now generating to actually navigate itself. So guys, that's just important to take note of. You know, this is a specific solution, you know, for underground mining, you know, especially stope mapping, but it can also be used, you know, for internal warehouses where you actually store your stock. Okay, so for stockpile reconciliation, this is ultimately where you would also be using this specific system. The thing is for outdoors, because it's not really capturing the information. Remember the whole, I'm going to say the benefit of the system is that it can do it autonomously. But for that, it needs basically features. It needs point cloud data to actually be able to navigate itself. It's difficult in a surface scenario. You wanted to use it in an indoor scenario.
And I see a question came in.
Good question. Thank you for the question. Awesome. I think that was from
the water surface. Yes. So how does the drone handle water? Essentially, if there was a pool of water, if it's very dark, it would be able to reflect the points off the surface of the water and identify it as obstacles. So it wouldn't just fly into the water. And we also have software implementations in place where you can actually block off an area that you don't want the robot to fly close to or into a certain area. So there's a few different ways, but water in terms of pooling water or water surfaces is no issue for the drone. It's able to fly over water, pooling water, over different water surfaces without issue.
Great. Thanks for that question, Jacoba. Nani? Yes, you've got another question?
Yes. In terms of safety, do how do you prevent it from crashing onto the walls? Do you have a proximity detection, or you just rely on the flight plan?
So the entire premise of the flight plan is designed around, it generates its own flight plan based on the obstacles it sees. So the robot picks up, for example, walls, surfaces, cables, identifies that as an obstacle and knows to simply go around it. So let's say there was a very small hole that was too small for the robot to go into. It won't simply fly into the wall. It will identify that there's obstacles in the way. It can't enter that space, and it will turn around and come back home. So yeah, it's not going to hit a wall or fly into any surfaces whatsoever. As you saw, the volume I gave it was just a generic volume, but it came up with its entire flight path fully autonomously. So that's fully based on the algorithm itself, the SLAM algorithm, but it's able to identify surfaces, determine a certain factor of safety, and make sure it doesn't fly too close to any obstacles or anything that's in the way. So yeah, it won't fly into a wall.
Nani, what we're going to do also is let's quickly move over to just showing you guys the point cloud that it actually has generated, and then also just show you how does the robot actually, it builds blocks so that it actually knows what is the safety factor it needs to maintain to actually do the flying part. So Joel, can you maybe just show that part, please?
Yeah, so this part specifically will kind of show you an understanding of the algorithm a bit better. So here I'm starting the LiDAR. And you can see that in real time, some points are being collected. And this is the point cloud. This is the data that you're looking for. You're going to be using this data. And you can see that the robot generates this point cloud itself. And it's the very detailed, this is the detailed look, right? Well, now I'm going to open up this filter called the occupancy grid. And this is more internal. It's not something you might look at as much, but this is to understand what the robot sees as obstacles. So any cubes you see here is called a voxel. And that's essentially, once the robot picks up enough points from a certain area, it turns it into this cube, and this cube represents an obstacle. So you can see all the walls around the robot are cubes. And you might say, well, Joel, why is there points at the front of this point cloud, and these aren't cubes, because this is a wall? Well, because the robot's still far away from this specific area, it doesn't have enough points yet to figure out that it's an obstacle. Once it starts getting closer to an area, it'll fill in those points and it'll make it an obstacle. So now, lastly, how does it use this information to actually plan a flight path? I'm going to open up this third one. So now, if you take a look, you can see the blue cubes are much thicker than the actual point cloud. So again, if I switch off and then I open this back up, you see how thick this is. So now, the big space we had is a bit smaller. This represents, the blue cubes represent no fly space. It means the robot will not fly this close to this object. So it won't fly this close to this wall or to a cable, anything like that. Anything that's not a blue cube represents free space or safe space for the robot to fly. So now you understand how does it generate its flight path. It's based on what is an obstacle in the environment, and from that obstacle, what is my safe space? What is my factor of safety to stay far away or a good distance, safe distance away from a wall? Yes, so the robot does have a maximum range of 250 meters one way, which is a very big range for underground use. It's able to perform a full 250 meter scan, come back, so overall 500 meters round trip. But you might realize that that's very big for stopes. Oh, yes. So it doesn't just take the first scan into consideration. Once it's doing its scan, it's out into the stope. When it's coming back, it's recalculating that flight path. It's always deeming an environment to be a new environment. It's never going to assume that it's already flown somewhere. So if someone decides to step where the robot is supposed to be landing and they're standing in front of it, it's going to wait for you to get out of the way and eventually recalculate its flight path and land safely. So it's not reliant on anything that it's learned previously. It's always assuming that the environment is a brand new environment. So it's very safe for workers to be near the drone. It's able to identify that there's an obstacle, the obstacle being a worker, if the worker decides to go stand closer to the helipad, and it will wait for that obstacle to clear before actually coming back and land. So there's a lot of things in terms of how it plans a flight path, but I hope this gives a good general idea of exactly what's in the background.
Yes, Etienne, I see your hand is up.
Gustav and Joel, what is the minimum area required where it will go through? Is it a 3x3 box, a 1x1 box, or how does it determine it's safe for me to proceed into this area or not?
Yes. So it needs approximately 3 meters by 3 meters in order to fly into the space. It's actually a little smaller than that. We just advertise that as 3 by 3, but it can typically fit closer to 2.7 meters by 2.7 meters. Of course, it's an algorithm. So essentially those blue cubes I showed you, if a space was too small, the entire opening would be filled with blue cubes, and the robot would know that based on the safety features in place, it would not be able to enter that space safely, and it'll simply come back around and return home. So it needs to be approximately 3 by 3 meters in opening in order to enter. Yes?
Thank you. Once again, it seems like the new baby has got some limitations in terms of complete decision making. As you have shown from the last slide, that it determines the obstacle, it can avoid taking data from other areas that need water, or where it shows that the left leg is a blockage. It creates a gray area. How do you deal with those gray areas in terms of information?
I'm sorry.
I think it's blockages. Are you referring to difficult areas, smaller areas where there might be, where the drone can't actually get into, or are you referring to, let's say, areas where you couldn't actually get data in? What?
Yes, areas where actually the drone failed to get the data for the completeness of the wall.
Okay, so typically, stuff to take into consideration is typically, let's say, water, but it handles water pretty well. So Joel and the Exyn team has done several flight missions, all right? Because it's the way that it's actually exploring a stope, it basically makes sure that that whole stope is mapped out. In a specific, example that he showed, for instance, there was openings in the top of that stope. So the ExynAero system actually went to the top and actually explored those smaller holes to be able to generate a better true 3D representation of the stope. So it explores. That is what the ExynAero system does. That is what it's designed to do. Making use of the AI technology built into the system, that's how it navigates and making sure that you've got a complete 3D representation of the stope.
So it's going to find those shadows. It's going to go and fill those in. Okay. As long as it's able to fly into those spaces, it's designed to recognize what a shadow is and go fill it in. There's a full thing I could show you, but it's very technological. But it understands where the shadow is.
And afterwards, we're going to show you guys an example where it was quite a complex flight. I'm going to leave Joel to just show you guys that. I think the fact that if you can see what it can actually do and how it explores, that will basically kind of answer that question.
So we're going to touch base first on georeferencing, and after that I'm going to show you a real-life example of a real scan in a mine and the GoPro video that was attached to it. So you're going to get a full idea of how it maneuvers.
Before we just move on, I see we've got a question from Matsapa. Matsapa, yes, you can go.
Afternoon, gentlemen. I just wanted to understand, I didn't get you well on the flight path. We are mining coal as room and pillar. So I don't know if it just create its own path, or you have to design the flight path around the pillars. So whatever, does it follow one channel, or it goes from one tunnel to another on its own?
Joel, yes.
Yes. So a room and pillar mine is a perfect example of an explorer. It generates a full flight path on its own, and it'll go around those pillars fully on its own. You don't need to give it a direct flight path. You don't need to say, hey, go behind this pillar. It's going to go all around every single pillar and generate a scan entirely of the room and pillar area that you're in. So it generates its full flight path solely based on that volume I gave it. That's where the autonomy comes in. That's where the AI comes in. It's able to identify the environment, figure out where it can fly, figure out where it didn't fly yet, and where it needs to fill in data, and it's generating that flight path fully autonomously on its own. You don't need to give it any information whatsoever. I hope that, does that answer your question?
Okay. Yeah, Matsapa, so ultimately you have to define that, basically, look at this as your parameter box. You need to define the area that it needs to fly in. It's not going to fly outside of that area. So typically in the block and pillar method, you need to define the area and it will navigate within that area and actually map out that certain area.
I even have a room and pillar mine scan I can probably show after this presentation.
That would be great. Thanks,
So if
Joe.
you want to see it in action in the room and pillar mine, I'd be more than happy to showcase that to you.
Thank you.
That's good?
That's perfect. Thanks.
Perfect. So let's get into georeferencing. I'm going to be using a real-life example of a scan that was performed last summer. So simply all I would do after the flight is I would go here and download my flight directly from my robot. It's simply a press of a button, and it takes approximately half the time that it took for the mission. So you might be waiting a minute, and that data will be all completely transferred from the robot, from the drone, to your tablet, to your workstation. So you'd have it in this software now. So now let's take a look. I'm going to open one of those files just for you to see an example here. All right. All right, so this was a stope scan, a very different stope, as you can tell. But this was a scan that was performed underground. And I'm going to go over here. So you can see all the people standing here. This was approximately the takeoff area. And we're going to proceed with georeferencing. So all it would do, I'm just going to close this off. We don't need the full point cloud. I would simply open a survey control point file. So if you wanted to georeference, which you don't need to, by the way, but if you wanted to georeference your scan, you simply install 4 wall markers, your survey stations, at the takeoff area. And then you take those coordinates after the fact and simply put them into our software, import them into our software very easily, just like I'm doing right now. I choose my order and my units. In this case, it was XYZ and meters. I'll press the OK. From here, all I do is I press the Detect Survey Targets. You wait a second. And once it loads in, we're going to be able to see where exactly the survey markers were and identify and proceed with our georeferencing. So you can see for this, I was here. I was the one conducting this flight. We had only placed 3 wall markers in this specific flight. But the fun thing is, you can see that the robot thought that maybe the headlamps are maybe possible survey marker locations. So this is, again, fully autonomous. It's an algorithm that recognizes the wall marker on its own. And you can see I put 1 here, and then I put 2 more on this side, but I don't know which one it is, right? There's 3 here. So there's something that was shiny or that had high reflectivity that's being possibly recognized as a possible target. So now you might think, oh, I'm going to need to actually figure out which one it is. Well, you don't. All you have to do is press the georeference button and let the software come up with its own calculations. And using the file you put in, it's able to come up with the triangulation and calculate which ones are the correct stations. So as you can see, I pressed the georeference. It told me it completed it successfully. It's able to identify this station as being the number 2 station, 3, and 4. So we only used 3. And here, we're done georeferencing. It was a very simple, streamlined process. From here, I can export my point cloud. I can put in a couple different parameters if I wanted to spoon the point cloud, which is just kind of cleaning it up. I can also subsample it if I want to reduce the number of points, make it easier to use in your mining software. And from here, we're pretty much done. I would press the OK button, press Save, and I could transfer this point cloud data into any mining software that you might be using, whether it be in LAS format, PLY format, XYZ format. You're able to import it into virtually any single mining software there is out there and use it fully georeferenced. So if you import it into your software, you'll see it'll kind of just line up and match up exactly where it's supposed to be in your mining environment on your software. Any questions on the georeferencing so far? It's a very easy process.
Right. Okay, Joel. Yeah, we can move on.
Good.
Yes.
Perfect. So let's move on. let's showcase some actual real-life examples of a flight being completed. So I'm going to open again my software, the ExynAero software, and we're going to play back a flight that was performed. So just bear with me. I'm going to open it up here on my computer. Here. And I've done a lot of flights, so I need to, there you go, this is the one we want. Perfect. All right. Bear with me a second. All right, here we are. So here we're going to take a look at an actual flight, and this is exactly the data that the users saw in real time as they were performing the mission. So now you see they started their scan. You can see the opening here. And you can see the robot is going to, again, this is an Explorer. All we did is a big box here. I'm telling the robot, figure out your own flight plan. So it's going to do this fully autonomously on its own. You can see it's going to enter above this obstacle, around these cables, all in real time. You can see this in real time as it's happening, over the berm, between the cables here. It's able to fit itself within this very small environment. You can see the point clouds start generating in real time here. Hundreds of thousands of points coming in. Now let's take a look. We're going to zoom in a little bit more. As you can see, it's able to identify cables, go around the cables. I'm going to speed up this playback a little bit so it doesn't take as much time. And I might slow it down a little bit towards areas of interest. As you can see, it's going around this cable. You can see all the meshing, the rebar here. So I'll slow it down again so we can kind of take a look at this environment. As you can see now it's identified a pocket that it hasn't scanned yet, so it's going up into the stope. You can see the great detail of the surfaces, the cables. It's able to identify this obstacle, not run into it, simply fly around this obstacle without issue. See now it's going to go back towards another pocket that it deems that there's a shadow it wants to scan. So again, we'll put it back to 2 times the speed until we get somewhere a little bit more interesting. Now it's going to go down into this area. Make sure you pick up all the shadows. So it's going to go down into this crevice over here. No problems at all, going around the cables. And of course, again, this is fully autonomous. No flight path given, no GPS. We even lost connection at this point. It's a fully autonomous flight. No input required. No one's actually maneuvering this unit around. So now it's going to the opposite side of this big environment. I would call it, it's not even called a stope. I would say this is just a large Explorer area, a massive underground cavity. As you can see here, it's going up into this pocket. And you can see there's even a pocket back here that users didn't even know existed, or so the mine operators didn't even know was there. It's able to identify all these obstacles. And it's essentially done its mission. Now we're going to play it a little quicker. I don't want to take up too much of anyone's time. You can see it's entering this very small pocket. And identify this pocket that no one even knew existed in this mine. So it was pretty brand new for them. They didn't see this. You can even see it's going around these obstacles, coming up with its full entire flight path. So you see how comfortable it is flying around cables, around these obstacles. There's no way anyone would be able to fly this manually and perform this mission. So you can see just how much data we picked up here in this short flight. Of course, this would be pretty much impossible with a traditional CMS system. And the robot has pretty much done its mission here. It would essentially just come back home and land once complete. So I think I'm going to cut it off here, and we're going to take a look at the GoPro video. But if we want, we can take a look here. It's going to go back home and land. It's on its way home now. It's deemed that it's done scanning this environment. It's scanned as much as it could. It's going to enter back into the small pocket where home was. You see it's able to maneuver inside this environment. And now you can see where everyone was standing. So here we are. And apologies if it's a little laggy. It tends to happen sometimes with Microsoft Teams. And it's going to land here on the spot it took off. And we're done. So one quick mission, able to capture everything. So now we're going to move over from this point cloud view, and I'm also going to show you the exact same flight, but from the GoPro perspective. So you're going to get to see what it looked like in real time. So here we are, the robot takes off, and this is the same area we just flew in. You can see with the GoPro, the robot was able to maneuver here inside this space, around these obstacles. And then I'm going to cut ahead a bit because it is a rather large video. So we're going to want to fast forward to a little bit of it, make sure that we don't, I don't want to take 8 minutes to show it to you. But you can see the obstacles. You're going to be able to see some veins, even some ore in the walls. So for geology departments, this is quite useful. So you can see the robot's able to capture video data here. You can see the ore in the wall here, different strains, the meshing, all that visual information. That this, along with the point cloud you're capturing, you're really getting a full 100% idea on what your environment looks like. So you can see here it's capturing different videos of the various environments it's flying in. We're going to cut ahead also here. Again, you can see here the ore. So this is copper strain here. Maneuvering these tight environments without issue. See here it's entering this smaller pocket, identifying obstacles, staying within it. This is the pocket I was talking about where we didn't even know existed. So it went inside this pocket here, raised itself into the pocket, and then you're going to see cut a little forward, even some more ore here. Pocket here we saw earlier with all the obstacles, all the objects flew. There we go. So we're going to cut it off here, I think, as this gives you a really good idea of exactly where the robot maneuvered. And the first-person view video you were able to capture at the same time. Before we move on to room and pillar and all that, is there any questions so far? I hope this gives a bit of a clear idea exactly of a real use case and how the robot maneuvers. But is there any questions from the audience?
Right, yeah, nothing, Joel. I think, yeah, let's maybe show that the block and pillar as a demo that you guys did. I think that would be great.
Okay. Take a look. Bear with me here. Locate it here. Let's see. Look, I might have to download it, so I might not have it available right away. But I would be more than happy to send him a video if you'd like to see it.
Let's
yes, send me a link also.
Yeah, sorry guys. Yeah, so we'll have to download the data first. So sorry, it's not readily available, but ultimately we can definitely share it with you guys afterwards. Guys, the recording will be available. We can actually share that data set as well. Maybe just the typical sample data set of the actual block and pillar method. Is there any last questions? So guys, I think ultimately that specific data set that Joel showed really shows the complex scenarios that the system can actually operate in. You know, how it explores those smaller pocket areas, depending on the shape. It's really kind of a tool that can be used to really kind of get to that true 3D representation of your stope. Yeah, ultimately, and also having a actual sample set to show you the complexity in which it can actually operate in. So I don't know if there's any last questions, guys, before we move on. I think it's
maybe just something from my side. It's Shane here again. So perhaps maybe just for everyone on the call, we have ordered our Exyn drone from Exyn Technologies. We are hoping for the drone to arrive very soon. And if there's any engagements that you want to have with us privately, please, you're welcome to communicate with us. If we have to set up demonstrations for yourselves to see how the drone performs, obviously that's also welcome for us to engage with you on that level. I think each and every one of you on this call is people that are communicating on a daily basis. If there's any questions that you have, please reach out to me or any one of us on the call here, and we can then definitely make sure that we provide the necessary information or set up these sessions, what we are hoping to have for yourselves to experience the technology. Thank you very much.
Perfect. Thanks, Shane. Yeah, guys, I'd just like to also make use of this opportunity. So Etienne Coetzee and Leon Reinders is on the call. They're basically our Africa sales consultants. So please feel free to reach out to our African sales team. And yeah, guys, we just wanted to use this opportunity to showcase the technology. And yeah, I hope to see and to be on your side soon. And yeah, so if there's maybe any last questions, please feel free to, any last comments or questions, please feel free to kind of, yeah, ask them. And yeah, I think that is basically it. So guys, yeah, from my side, thank you so much for attending. And really thank you for the opportunity. Thanks for taking the time out of your busy schedule to be on this call. And yeah, as I've mentioned, the recording will be available. I'm going to be on the call, so please feel free. If you need to leave, you're more than welcome to then now log off. Have a great day, guys. And Joel, thank you so much. Thanks for being here. And have a good one, guys. Till next time.